This video shows you how to compute impulse response functions of a VAR1 model, and the system we assume has k variables, where k is larger than 0. So as the VAR1 model is only a vectorized version of the AR1 model, it might be easy for you to note that the IRF takes that simple form here, where the IRF for period j is simply a to the j times c, and j is 0 or larger than 0. So note here the IRF of j is a k times k matrix, a to the j is k times k, and the vol matrix C is also k times k. A recursive and hence fast algorithm for computing the term structure of IRFs, meaning determine the IRF for different j's, is as follows. The IRF for j periods ahead is simply a times the IRF of j minus 1 periods ahead, and the initial condition is that the IRF of 0 is the volatility matrix C. Notice the IRF of j aggregates information about the persistence of the time series, that's essentially captured by A, and about the volatility matrix C. The immediate impact for j equals 0 is only affected by the volatility matrix C. In contrast, the very long-term behavior of the system is mainly affected by A, namely the persistence matrix of the system. So if the maximum eigenvalue of matrix A is smaller than 1, the IRF of j reverts to 0 for large j, which implies that the system is stationary. This says that shocks to the system have only a transitory impact, but not a permanent one. So importantly for the computation, note that the IRF of j, the way I've been writing it, is a k times k matrix. So what you have to do in addition is to specify the shock that you would like to feed through the system. Let's call that shock eta. Now the classical way is to look at a 1 standard deviation shock at a time. Let's have an example. If k was 2, so you have a 2 variable system, and you would like to understand how a 1 standard deviation shock in the first variable affects the entire system j periods ahead, you simply compute the product of the IRF j periods ahead times a column vector which would be 1, 0. The 1 stands for the 1 standard deviation shock in the first variable, and the 0 stands for a 0 standard deviation shock in the second variable. Now the product will be a column vector, and the first element of that column vector gives you the j period ahead response on the first variable, while the second element gives you the response on the second variable. As an additional example, you might want to know how a 2 standard deviation event in the first variable, together with a 1 standard deviation shock in the second variable, affects both variables of your 2-dimensional VAR1 system. So essentially, you compute the product of IRF of j times the column vector, which has now the parameterizations 2, 1. I want to end this video with a word of caution. Investors work with IRFs because they extract information from data that quantifies how different variables are expected to change as a response to an unpredicted shock in one of the other variables of interest. Now there's a problem here, namely the impulse response function of a VAR system is not necessarily unique. That means there is an identification problem. And that is clearly disturbing for investors, as they want a unique response. Now the identification problem can be solved if additional restrictions are incorporated. But before we move on towards such restrictions, I want you to understand the cause for that identification problem. So for that, assume that you observe a time series xt, which we assume follows a VAR1 model with the following shape. If the OLS assumptions hold, and if you have no further constraints on the parameters, you can conveniently run OLS equation by equation to identify all the parameters. So as a result, you will determine the A hat, epsilon hat, and the sigma hat. And note the sigma hat is the OLS estimate of the error covariance matrix. And now here note, the covariance matrix is symmetric, implying the correlation of x1 with x2 is the same than the correlation of x2 with x1. And that highlights what you know, that correlation does not reveal causation. Hence, additional exogenous causality restrictions are necessary to uniquely identify the IRF of the system. And any such restriction has to specify which shock made another shock move. So what's the causality? And here it's very important to remember and to understand that good restrictions are grounded in economic theory, or at least in market experience.
Got feedback? We would love to hear it. Please drop us a line. And if you liked the video, give it a thumbs up. And don't forget to subscribe to the channel.